This conference will now be recorded.
Very good evening, students. We have been discussing waves, last chapter of this 11th standard. So, in the last class, we had discussed little bit about speed of transverse waves in a straight string. Today we'll recap that and we'll learn furthermore like transverse waves in a solid medium, like speed of transverse waves in a solid medium. Then we'll further learn speed of longitudinal wave in a liquid or gas, Newton's formula for the speed of sound in gas and Laplace's correction to that. And we'll take up few numerical problems on this. So let us learn speed of transverse wave in a straight string. So we know that the wave velocity through a medium depends on its inertial and elastic properties. So these two things are very basic things. The speed of wave in any medium depends on the inertial. First is inertial and the elastic properties. So these two properties are important because these properties are actually defining the characteristics of the medium. Inertial property, let me write again. Inertial and elastic properties. So when you talk about a straight string, now let us take a straight string. We need to see what are the variables or what are the quantities which are related to inertia and elastic property for a straight string. So for a straight string, inertia is actually related to, anyway the inertia will be always related to mass, or mass is corresponding to the or the cause of the inertia. So we have to first of all take care of mass per unit length. Mass per unit length or linear mass density. You might be surprised Why I'm talking this? Because the speed of wave in a straight string will be depending on the inertial property and elastic properties. That's why we need to take care of the inertia part and the elastic part of the straight string. So inertia part is actually characterized by linear mass density or mass per unit length. Mass per unit length can be written as small m, so that can be written as capital M, that is the mass of the whole string by length. So the dimension of this mass per unit length will be m L to the power 1. This is the dimension of the mass per unit length. Okay, mass per unit length is having dimension m L to the power minus 1. Now, how the elastic properties is taken care in case of straight string, that is with the tension in the string. If the string is not elastic, you will not get any tension in that, because that will break easily. So tension in the string is denoted by capital T. And what is the dimension? What is the dimension of this T? Actually, tension is nothing but a force. It has a dimension of force itself. So we can write ml T to the power minus 2. Okay, this we can write. Now look, I'll use this empty space. Now if I take ratio T over M, then what we get? T is ml T to the power minus 2, and here this is ml to the power minus 1. Okay, so this will give you L to the power 2 and T to the power minus 2, right? Okay, so I'll remove this portion a little bit. So we have got the ratio of T to the mass per unit length. So ratio of tension to the mass per unit length is L square T to the power minus 2. Okay, so I'll remove this part also. Now, what is the dimension of speed or velocity? Dimension of velocity is given by L T to the power minus 1. Okay, so from these two, what we can write is that V, the velocity is, see, velocity will be proportional to square root of T by M. If you agree with me, then it will be good, because see, from here I am writing T by M. T by M has ratio L square T square, so I'll just write it. So which implies that square root of L square minus T to the power minus 2, which will be proportional to L T to the power minus 1. Okay, so from there I am just writing, but this is not required to write. What I'll do, I'll just come to an equation form So if you want to write an equation, you need to have, okay, k I'll be writing for some other things. So let me take the constant to be the c root over t by m. And it turns out that the dimension of this is 1. Okay, or the value of this is 1. So therefore we get the velocity of velocity of transverse wave. Let me erase this part, or let me erase everything. So we have already got that v is c root over t by m, where t is the tension, m is the mass per unit length, and this has dimension 1. So we can write v is equal to root over t by m. So this will give you the speed of, this is actually the speed or the velocity of wave. Velocity of what kind of wave? In a string, what kind of wave you expect? We have already discussed. So you expect transverse wave. So wave is propagating in this way, but the particles in the string is oscillating in this way, in the perpendicular direction. So it is a transverse wave. So velocity of transverse wave, velocity of transverse wave, velocity of transverse wave, therefore velocity of transverse on a straight string is given by v is equal to root over t by m, where t is the tension in the string, and m is the mass per unit length, mass per unit length of the string. Okay, so this is what we had discussed in the last class. Today we'll see transverse wave, velocity of transverse wave in a solid medium. In a solid, how do we describe, or how to express the velocity of transverse wave in a solid? So same thing, we have to take care two things. One is inertial part, inertial, and elastic properties, elastic properties. So these two things we have to take care. Okay, so in case of solid, the inertial part anyway will be taken care. So inertial part, inertial aspects will be taken care by the volume, sorry, density, by the density, mass density, mass density, this means it is actually volume density, not the length or surface density. So this is the mass density rho. Okay, that is m by v. So what is the dimension? We can write the dimension of rho. So m L to the power minus 3. So this is the dimension of the density. So how do you take care of the elastic aspect? So the elastic property, let me write, property is is represented by either the elasticity of shape or modulus of rigidity here with by rigidity modulus or modulus of rigidity. So elasticity of shape, elasticity of shape or rigidity modulus. So rigidity modulus, that is eta. And how do you define, like how to find out the dimension of this modulus? So it is stress by strain. Okay, stress by strain. It is for any type of modulus. Stress by strain. Strain is dimensionless. Uh, Sorry, this will have uh, so stress is actually mL to the power minus 2, that is the force per unit area. Okay, so in this case actually this is so force per unit area, this will be the stress, and strain will be actually dimensionless, so mL to the power minus, this will be dimensionless, this will have no dimension, strain, so it will give you mL to the power minus 1 t to the power minus 2. So this any kind of modulus will have the the dimension of mL to the power minus of 1 and t to the power minus 2. So it will have m L to the power minus 1 t to the power minus 2. This is the dimension. This is actually rigidity modulus. If in case of any modulus you take, this will be actually whether it is shape modulus or Young modulus or bulk modulus, the dimension remains the same. Okay, so now what we'll do, we'll take the ratio of this density and this uh, rigidity modulus. So because of less space, uh, there is a problem. So what we'll do, we'll just clean everything. Let us just write inertia denoted by and it has dimension m L to the power minus 3. In short, elasticity 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 here will denote elasticity or represent elasticity by rigidity modulus. So what will be the dimension? M L to the power minus 1 t to the power minus 2. Now similar thing we'll do here. We'll take the ratio ratio of eta by rho, and it would give you m l to the power minus 1 t to the power minus 2, and here m l to the power minus 3. So this will give you again l to the power 2 and t to the power minus 2. So we can say that the velocity or the speed of the transverse wave in solid is proportional to the ratio of eta to the power, sorry, eta to the density of the mass density of the solid. So eta it is the so the velocity excuse me, velocity or the speed of the transverse wave in a solid is directly proportional to the ratio of eta to to rho. Okay, so here also if we take the proportional constant c, this is eta by rho, and it is found that this is having dimension 1. So then what we get, v, that is the speed or the velocity of transverse wave in a solid, will be given by eta square root of eta by rho, square root of eta by rho. Okay, so you can solve numerical examples from your textbook or many other practice books. Now we'll learn the speed or the velocity of transverse wave, sorry, longitudinal wave in a liquid or gas. Speed of longitudinal wave in a gas. So in a gas or liquid. So what is longitudinal wave? We have already discussed. If the wave, okay, so or the disturbance propagates in such a way that that the direction of vibration of the particles of medium of medium is particles is in the direction perpendicular to the perpendicular to the direction of propagation of the wave, direction of I'm sorry in the direction of propagation of the wave itself. Okay, direction of propagation of the wave itself. And we have seen that the wave in that case propagates through compression and rarefaction of the medium. This we had already discussed earlier also. So this is actually longitudinal wave. Longitudinal wave. So in longitudinal wave, it is seen that the material medium particles in the medium vibrates in the same direction as the direction of propagation of the wave itself. In this case, suppose there is a air column which is a gas. If you vibrate a tuning fork, the air column very near to the fork will be first compressed, and because of compression, what will happen? Compression means change in density. Density changes because of compression or rarefaction. Density changes, so rho changes, and we know pressure is directly proportional to density. Directly proportional to density. So when there is a rarefaction or compression, there will be change in the density in the medium. Okay, and because of that, there will be a change in the pressure, and that's how longitudinal wave propagates in a liquid or gaseous medium. So we'll now see, if you want to visualize a little more about longitudinal wave. See, this is the rarefaction. This is the region of compression. Again, rarefaction. So actually what happens when the medium particles are compressed, the density increases. So the particles from here will try to go to the rarefied region where there is less density. So therefore particle will move in this way, and eventually this region also will get compressed because there will be more density because the more particles are coming over here. Thus, when the particle moves from here to here, this region will become rarefied and this region will be becoming compressed. So this is how compression and rarefaction, these are traveling along the direction of this rarefaction and this rarefaction and compression are the traveling along the direction of propagation of the wave itself. Okay, so this is brief idea about longitudinal waves. Now the when you talk about the velocity velocity of longitudinal wave in some fluid, whether it is liquid or gas, as the density changes, so we have to take care two things, as I said. So elastic part or elasticity will be taken care by the, so density changes means volume changes, so it is actually related to the bulk modulus modulus K. So it is actually characterized by bulk modulus K, and it is sometimes called kappa also, bulk modulus kappa. And the inertial part is actually taken care, inertia is taken care, density, that is the mass per unit volume, unit volume of the fluid. Now we know that K by rho, this obviously will give you the dimension of L square t to the power minus 2. So therefore, we can write same story here also. The velocity can be written as K by kappa by rho, where K is the bulk modulus of the gas or the fluid, bulk modulus of the fluid, okay, and this rho is the mass density of the fluid, okay. So this is how you should remember when longitudinal wave is propagating through a gaseous or liquid medium, the velocity can be expressed, or velocity of longitudinal wave will be equal to square root of kappa by rho. Kappa is the bulk modulus. Now, speed of longitudinal wave in a solid medium. How it will be in a solid medium? See, in a solid medium, if we just say an arbitrary solid, if I take an arbitrary solid, it would have actually uh, both the modulus, like bulk modulus and rigidity modulus, because for an arbitrary solid, velocity of the longitudinal wave can be written as for kappa plus kappa plus 4 by 3 into eta divided by rho. So this is for general solid in general. But if we have to find out longitudinal speed of longitudinal wave in a solid rod, in that case, so elastic part will be taken care. Longitudinal rod means what? It has expansion or compression in the lateral dimension or lateral direction, or in other words, the change in the lateral dimension will be negligible than the longitudinal change, okay. So we can consider just Young modulus, that is delta L by, sorry, that is F by A stress divided by delta L by L. Okay, this is the only change in the length. We are not considering the change in the breadth in case of elastic rod. Okay, in general, if we take the solid, this is the expression for the speed of the longitudinal wave within the solid, kappa plus 4 by 3 eta whole divided by rho. Rho is the density, mass density again. Okay, now if we take a rod, then you have to just consider the Young modulus for the elastic properties. So ml, anyway, the modulus has the same dimension, and again you have to consider the inertial part. So inertial part is again taken care by the density. So density means ml to the power minus 3. So similar, like same story. So here, if we take the proportionality constant to be 1, then the velocity or the speed of the longitudinal wave in a solid rod can be found out by this relation v is equal to square root of gamma by rho. Sorry, this is y Young modulus. Okay, y by rho. Okay, y by rho. So this is the speed or the velocity of longitudinal wave in a solid rod. Now let us find out the formula for the speed of sound. We have learned speed of longitudinal wave in a gas, but not of sound. So now we are finding out, or we are learning Newton's formula for the speed of sound in gas. So speed of sound in gas. So speed of sound in a gas. Sound is one kind of longitudinal wave that we know. Okay, so you have to take care whenever we are talking about gas, you have to take care the density part as well as the pressure part. Okay, so here Newton gave a formula for the speed of sound in a gas. So he argued, or he assumed, that the sound wave travels through a gaseous medium in isothermal condition. So Newton assumed that the sound wave propagates in a gas, propagates in a gas in isothermal condition or at isothermal condition. Isothermal condition. Isothermal condition. Okay. So you have to see we have got velocity in gas kappa by rho. That is what we have got. If you see kappa by rho, longitudinal wave in a liquid or gas, where kappa in this case will be kappa in this case will be isothermal. So bulk modulus, isothermal bulk modulus. Iso means isothermal bulk modulus. Bulk modulus. Okay. So if you want to find out isothermal bulk modulus, then you have to consider gas as an ideal gas. Sorry, yes, you have to consider the gas to be the ideal gas. So for an isothermal change, thermal change, for an isothermal change, we can write PV is equal to constant. Okay, so we can write P dV plus V dP is equal to 0, or P dV is equal to V dP minus V dP. So from here, look, if we go here, okay, let me clean this portion a little bit. So bulk modulus means bulk modulus means dp dv by v. Okay, so this is what we have to find out for isothermal change. And for isothermal change, we know for an ideal gas PV is equal to constant. So for that case, we can find out the phi is equal to dp by dv by v. See, we can write from here. The v are actually the velocity, not velocities here. These are volume. So this is the ideal gas equation. So from there, we are just getting pressure. P is equal to minus dp by dv by v, which is k iso. So k iso is actually given by the pressure. So we can write the speed or the velocity of sound in gas to be equal to k iso, which we have got as P pressure divided by rho. Rho is the density of the gas. Okay. So according to Newton's formula, if we find out the speed of sound in air, so in STP, standard pressure and temperature, what we get? So of sound, speed of sound in air at STP. If you write the standard pressure and temperature, see standard pressure over here, and this is the density. Density we know for air. So STP pressure will be 1.013 Newton per meter square or Pascal. Sorry, this there will be 10 to the power 5 if I write Newton per meter square. Okay, Newton per meter square. And density of air is 1.293 kg per meter cube. Okay, now if you take the ratio over here, you'll get nearly 280 meter per second. But this is not the actual value which you get experimentally. So this does not agree with the experimental value of the speed of sound in air, that is 333 meter 330 or 331 meter per second. Okay, meter per second in air, actual value. So there must be something wrong with this formula, so which we have written here. According to Newton, the speed of sound in a gas is given by V is equal to square root of pressure by density of the gas. Okay, but it is, if we use this formula to find out the speed of sound in air, we are getting only 280 meter per second, whereas experimentally the speed of sound in air is found to be 331 meter per second. Now Laplace has found the fault in Newton's formula and he had corrected it. We'll see what is the correction given by Laplace. So the correction given by Laplace is that when there is compression and rarefaction, and again compression and rarefaction happens in the medium, the heat or the temperature which is generated according to Newton, it is transferred to the rarefied region. Actually here the temperature, suppose this is compression region and this is the temperature in the rarefied region. So in general temperature there will be, since here is a compression, so there will be heat generated, so temperature will be more over at this compression region compared to this rarefied region. So according to Newton, this temperature will easily go to the extra heat, extra amount of heat will just immediately go to the rarefied region and equalize the temperature. Okay, equalize the temperature. This is the way in which you get the propagation of wave in isothermal process. So this is the way Newton thought. But what Laplace is saying is that this compression and rarefaction is actually very instantaneous phenomena, or it happens very quick. It happens very quick, and any quick process cannot be ideally isothermal. There will be some changes in the temperature. So this rarefaction and compression happens very quick while the sound propagates through the medium. Therefore, temperature cannot be equalized that within that fraction of time. Okay, within that fraction of time. Because of that, temperature in, at the compressed region, at the rarefied region will be different. So that's how Laplace argued that the propagation of longitudinal wave in gas, sorry, this is sound wave. Anyway, that is also longitudinal wave. So sound wave in a gas is an adiabatic process, not isothermal process. Okay, an adiabatic process. So we know this velocity is given by P by rho by Newton. This is according to Newton. So what is the, I'm sorry, this is given by, yes, but what is the main formula? We have to find out K adiabatic here. Adiabatic by rho. Rho anyway doesn't change. Adiabatic, K adiabatic. We have to find out the adiabatic bulk modulus. So how to find out? We know P v to the power gamma is equal to constant. So from here we can find out P gamma P v to the power gamma minus 1 dV plus v to the power gamma dP is equal to 0. Okay, so from here let us see what we can do. We have to find out K. K means we know dP by, so let me write gamma into P v to the power gamma minus 1 here into dv, that is equal to v to the power gamma minus v to the power gamma dp by dp. So from here further we can write p is equal to minus, let us say, gamma divided by, here this is gamma dv divided by, okay, so along with this itself we'll get v to the power gamma minus of 1. So we can write this as dp by v to the, so dv by v, dv by v from here, and along with a gamma over here. So p we get as k by, so better to keep here gamma into p, gamma p over here. So here bulk modulus in adiabatic process is found to be gamma into p. So you can do it in cool mind freshly, then you will be able to find out that the adiabatic bulk modulus to be gamma into p. So instead of p pressure, it is gamma into p. Therefore, according to Laplace, according to Laplace, velocity will be given by gamma p by rho. So what is gamma? Gamma is the, we have learnt already, Cp by Cv. Cp by Cv. Gamma is Cp by Cv. We have learnt in thermodynamics and kinetic theory of gases also. So Cp by Cv. Now, if we take this formula, Laplace's formula of speed of sound in gas, gamma p by rho. Now gamma for air is 7 by 5, 7 by 5, and p as usual we can write 0.13 into 10 to the power 5 meter per Newton per meter square. And if you put the density to be 1.293 kg per meter cube, it is found that the velocity will be nearly equal to 331.3 meter per second. 3 meter per second. So it is actually very near to 331 meter per second, which is the experimental value of the speed of sound in air. So Laplace's correction is justified. That means the speed of sound, or the sound propagates in air in adiabatic way, or the propagation of sound wave in air is an adiabatic process. So this is how we have learned today how longitudinal wave propagates in solid, liquid, and how sound wave propagates, and what are the corresponding speed of longitudinal wave in liquid or gas, in a solid, and Newton's formula for speed of sound in gas and Laplace's correction, etc. we have learned today. I'll stop it here for today. Next day we'll see the effect of speed of sound on various facts like density, pressure, temperature, humidity, etc. And along with that, we'll take up numerical examples because we have already covered many things here, including displacement equation of propagation of propagating wave, etc. And we have learned various terms like amplitude, wavelength, time period, frequency, etc. So if the equation of displacement of a propagating wave is given, how to find out all those corresponding quantities we'll learn tomorrow while discussing numerical problems. Okay, so bye for today.